Hello there and welcome back to the Science Sleepy Minds. Tonight, you're drifting through a universe that's getting roomier. Not in a relaxing, decluttered living space kind of way, but in a literal, everything is getting farther away from everything else kind of way. You hover silently, weightless, while galaxies, beautiful spirals and ghostly smudges seem to slide away from you in every direction, like marbles slipping off an ever-expanding trampoline. It's quiet, cold, and beautiful. And you probably won't survive this, by the way, just in case you were planning to hang out near a red giant or something. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And as always, I'd love to know where you're tuning in from and what time it is. Drop that in the comments below. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're moving? Well, technically, everything is. The universe itself is swelling like dough left in a warm kitchen. Every pocket of empty space, every yawning void between galaxies stretches just a little bit more with every second that passes. It's so subtle you wouldn't feel it on Earth. You won't wake up tomorrow taller because the atoms in your spine decide to space out. But across billions of light years, that expansion becomes undeniable. This wasn't always obvious. For a long time, people assumed the universe was stable, unchanging, kind of like an eternal snow globe that had already settled after the first shake. Ancient cosmologies, from Mesopotamia to medieval Europe, pictured the cosmos as a fixed, tidy thing, with stars pinned to crystal spheres, maybe a god or two holding the whole thing together with divine duct tape. But here you are, watching galaxies fade into the darkness, not because they're dying, but because they're running away. And the farther out you look, the faster they go. It's not them moving through space, it's space itself stretching between you and them. Now, if this feels like it breaks some kind of cosmic speed limit, it kind of does. Galaxies can appear to recede faster than light the farther away they are. But this doesn't violate Einstein's rules, because they're not zooming through space. Instead, the space between you and them is expanding. No one's cheating, just using the loopholes in the laws of physics like any good cosmologist does. You coast past the Milky Way's edge, where familiar stars thin out and cold emptiness takes over. Out here, the view is humbling. Every point of light is a galaxy, each home to billions of stars, maybe trillions of planets. And still, the vast majority of the universe is emptiness, quiet, dark, and growing. This is cosmic inflation on the slow burner. Not the flashbang inflation that supposedly happened fractions of a second after the Big Bang, when the universe ballooned from subatomic to football field-sized faster than you can say quantum vacuum instability. No, this is the expansion that's been ongoing for 13.8 billion years, and what we once thought would slow down over time, like a ball tossed into the air, is instead doing the opposite. But don't get ahead of yourself. To truly appreciate the weirdness of this accelerating expansion, we have to rewind. Float backward through time, back before you knew what dark energy was, before anyone did. The year is 1929. You're now ghosting through the Mount Wilson Observatory, high in the San Gabriel Mountains. Inside, Edwin Hubble is hunched over photographic plates, quietly revolutionizing everything. This soft-spoken former lawyer, yes, he originally trained as a lawyer, has been measuring the redshifts of distant galaxies. He's noticing something strange. Every galaxy he studies seems to be receding. Not just some, all of them. The farther away they are, the faster they're moving. It's like the universe is stretching in all directions at once, and thus, a new idea is born. One that will slowly unravel our understanding of the cosmos over the next 100 years. But here in the present, you're floating again, weightless, staring into that ever-stretching darkness. The energy driving this expansion isn't from stars or black holes or anything visible. It doesn't come in particles or waves. It has no scent, no sound, no colour. But it has an effect, one so powerful it's rewriting our cosmic future. Here's where things get weirder. You might imagine that gravity, the big cosmic magnet, should pull everything back together, like a rubber band, stretching but wanting to snap. And for a while, that's what most scientists thought, that eventually the universe might slow down, maybe even collapse back in a fiery reversal called the Big Crunch Neat, symmetrical, like closing a book. Instead, we got a page-turner with no final chapter in sight. Because sometime around 1998, yep, that recently, astronomers noticed something deeply unsettling. The universe wasn't slowing down, it was accelerating, being pulled apart faster and faster by something we couldn't see, something we couldn't measure directly, and something we, rather unhelpfully, call dark energy. But you're not there yet. You're still floating in that inky space between galaxies, letting your eyes adjust to the scale, every point of light receding, every moment stretching farther than the one before, a silent, elegant drift toward what exactly? Cold nothingness? A shattering heat death? Or something no one's even guessed yet? Historians still argue whether humanity's shift from a static to an expanding universe was the most important scientific revolution since Copernicus politely evicted Earth from the centre of the cosmos. Either way, it marked a turning point. Suddenly the universe wasn't eternal and unchanging. It had a beginning, and now, maybe an ending. Here's a fun little fringe fact before you doze off. Some researchers have proposed that the universe's expansion isn't even real, but a perceptual effect caused by the passage of time itself changing. That time might be slowing down, not space speeding up. Now, is that probably wrong? Yeah. But in the game of cosmology, even the weirdest ideas get their 15 minutes of gravitational fame. So, back to the view. A galaxy just slipped out of sight. Beyond the cosmic horizon, never to return. And that's not poetic exaggeration. There are galaxies right now vanishing from our observable universe, carried away faster than light can chase them. Like a boat drifting over the curve of the Earth, except the Earth is the fabric of space, and the boat's being shoved by a force no one understands. The next time you look at the night sky, if your city lets you see any stars at all, just remember, you're peeking through a shrinking window, a vanishing glimpse into a vastness that's fleeing from your gaze. And the thing pushing it away, well, we're just getting to know it. You settle now into a slower drift, hovering just above the misty veil of time itself as you float backward through the early 20th century. The stars shimmer a little differently here, more local, more behaved. It's a younger universe and a lot less opinionated about expanding. You come to rest outside a modest dome tucked high in the mountains of California. Mount Wilson Observatory, year 1923. It's a chilly evening, and inside a man with an aristocratic air and a moustache that screams, "I make discoveries before breakfast," is leaning over a massive telescope. Edwin Hubble. You know the name, on satellites, school textbooks, maybe even a screensaver, but this is the night that everything begins to unravel. Hubble isn't alone, of course. He's been building on decades of work by other astronomers, Henrietta Leavitt, Vesto Slipher, and a whole catalogue of unsung stargazers who spent their lives squinting into the abyss. But tonight something clicks, something big. You glide behind Hubble as he studies one of the faint, fuzzy patches of light in the night sky. For years, people had argued about these spiral nebulae. Were they just clouds of gas inside our own Milky Way, or were they whole other galaxies unimaginably far away? Hubble squints at the photographic plate and sees something that settles it. A Cepheid variable star, essentially a natural lighthouse, pulsing with a rhythm that gives away its true distance. And this one is far, far too distant to be part of the Milky Way. In that moment, the universe goes from being our galaxy to being everything, bigger than anyone had dared to imagine. But Hubble doesn't stop there. Over the next few years, he starts plotting distances to galaxies, and he notices something funny. When he compares these distances to the redshifts measured by Slipher, those subtle stretches in a galaxy's light spectrum, he sees a trend. A wild, beautiful, unsettling trend. The farther a galaxy is, the faster it appears to be moving away from us. You hover over the graph that would change cosmology forever. It's simple, almost too simple, distance on one axis, velocity on the other. The result? A neat diagonal line. A law is born. The universe is expanding. Later we'd call it Hubble's law, though you could argue Slipher deserved half the credit and Henrietta Leavitt deserved a statue made of starlight. Historians still argue whether Hubble truly grasped the implications of what he'd found. Was he just noting a pattern, or did he realise he was holding a mirror up to the birth of the cosmos? Either way, by 1929 the astronomy world was on fire with the idea that the universe wasn't static after all. It was moving, stretching, blowing up from the inside, and the redshift, that tiny shift in light toward the red end of the spectrum, became the fingerprint of cosmic expansion. Imagine sirens dropping in pitch as they speed away. Galaxies, it turns out, do the same thing, except instead of sound waves, it's light waves, and instead of annoying traffic cops, it's entire galaxies hurtling away at thousands of kilometers per second. Here's your quirky tidbit of the night. Hubble wore a bow tie and carried himself like an Oxford scholar, but he was a bit of a drama magnet. He insisted that only he could use the 100-inch Hooker telescope at Mount Wilson, because apparently even in science, telescope envy is real. You leave Mount Wilson now, quietly drifting upward as the observatory fades behind the swirling curtain of time. The revelation of cosmic expansion is starting to ripple through the scientific world. And one very famous physicist is not thrilled. Albert Einstein, that wild-haired icon of relativity, had already built a beautiful equation for the universe, a model that balanced all the forces just so. But it predicted something annoying, that the universe couldn't stay static. It would have to be either expanding or contracting. Einstein, like most scientists at the time, found that idea uncomfortable. A dynamic universe felt unstable. So he patched his equations with a little extra term, the cosmological constant, a gentle, anti-gravity force designed solely to hold the universe in place. But now Hubble's data shows that the universe is expanding, and Einstein's fix suddenly looks like a cosmic goof. Legend says he called it the greatest blunder of his life, though to be fair, historians still argue whether he actually used those exact words, or whether that's just the universe's best PR spin. Either way, you can practically hear space-time itself giggling. What's important is this: the idea of a changing universe, an expanding one, had been unleashed, and there was no going back. The redshift wasn't just a curiosity, it was a clue, one of the first breadcrumbs leading us toward the terrifyingly huge truth that the universe has a past, a beginning, and if you're the dramatic type, an inevitable end. And here's a spooky little fact for the road. If you could somehow teleport instantly to a galaxy 10 billion light-years away and look back toward Earth, you wouldn't see our planet. You'd see the Milky Way when it was still forming. You'd see dust and fire and baby stars. Light takes time to travel, and that time becomes a telescope. Distance is vision, and redshift is our cosmic calendar. You coast again through space, watching the light from distant galaxies stretch thinner and thinner, like taffy pulled across unimaginable distances. You can almost feel the light aging as it moves, colour bleeding out, wavelengths lengthening like a scream echoing through deep water. We still use Hubble's law today, although it's gotten a bit more complex. We now talk about the Hubble constant, a value that tells us how fast the universe is expanding at different points in time. The only problem, we can't agree on what that value is. Even now, a century later, telescopes like the Hubble and the James Webb give us slightly different answers than those we get from studying the cosmic microwave background. Historians still argue whether this Hubble tension is a sign of deeper physics we don't understand, or just a really annoying math error someone made in 2014 and never caught. So here you are, riding light waves from distant galaxies that began their journey when dinosaurs still ruled the Earth. You can thank Hubble and Slipher and Leavitt, and yes, even Einstein, for giving us the courage to admit the universe might be messier, louder, and more exciting than we ever expected. But remember, this expanding universe was supposed to be slowing down. Gravity should have been enough to eventually bring everything to a gentle halt, maybe even a collapse. But as you'll soon see, the universe had other ideas, and a name for those ideas? Dark energy. You drift now between galaxies slowly, dreamily, as if the whole cosmos is exhaling. Vast sheets of stars unfurl across the void like golden lace, delicate and impossibly huge. Here, in this frozen suspension, it's easy to imagine that everything will just stay, that the galaxies will keep coasting along, that their light will keep reaching us, that the universe will gently stretch, maybe even get bored of it and stop. Because that's what everyone thought for a while, that, yes, the universe is expanding, but gravity has a say in things too, and gravity, she doesn't like letting go. You hover near a massive galaxy cluster, a tangle of galaxies bound together by invisible threads of gravity. They swirl and tug at each other in a slow cosmic dance, distorted by lensing and thick with dark matter you can't see but definitely feel. It's mesmerizing. And you might assume that the same gravitational pull that holds these clusters together would eventually slow down the entire universe's expansion. That's what scientists believed for most of the 20th century. The expansion was real. But surely it was slowing. Slowing because of all the matter in the universe. Stars, planets, gas clouds, dark matter. Every galaxy pulling on every other, slowing the cosmic push outward like brakes on a runaway car. Gravity was supposed to be the grown-up in the room. They even had terms for how things might play out. Scenario 1, the big crunch. That's where gravity eventually wins, stops the expansion, and reverses it. The universe shrinks, gets hotter, denser, and finally implodes into itself in a cosmic do-over. Crunchy. Scenario 2, the flat universe, or sometimes the critical universe. Gravity balances the expansion just right. The universe coasts forever, not speeding up, not slowing down, just floating in a kind of elegant geometric limbo. Scenario 3, the open universe, where gravity is too weak to ever stop the expansion, so the universe stretches forever, slowing down but never quite halting. Think cosmic decaf. It just fizzles out eventually, everything growing colder and darker. These were the big options, the ones that professors drew on chalkboards and grad students built careers trying to model, and they all depended on one key thing: how much stuff was in the universe. Mass equals gravity equals slowdown. So, for decades, cosmologists were basically playing cosmic accountants, trying to tally up everything with mass, every atom, every star, every sneeze of interstellar hydrogen, to figure out the universe's total budget. Because once you know that, you can predict the universe's fate. But there was a problem. No matter how hard they looked, they couldn't find enough matter to make the equations work. Even after discovering dark matter, which, fun fact, outweighs normal matter by about 5 to 1, they still came up short. You float above the chalk-dusted desk of a cosmologist in the 1980s, papers spread out, calculator humming. There's this persistent mismatch between how much gravity we observe and how much mass we actually detect. It's like the universe is underweight, but still somehow trying to hold itself together. Historians still argue whether this gap in the cosmic ledger was what first nudged people towards suspecting something was missing, or whether it was just another unsolved headache to stuff in the "we'll deal with this later" drawer of physics. But gravity's still doing her best. You pass through clusters of galaxies that are bound tightly together, not by visible mass, but by the invisible grip of dark matter. It's a reminder that the universe is held together by threads we can't see. Still, the big assumption held: even with dark matter factored in, expansion should be slowing down. There were equations people trusted. You might even say bet their careers on. So the plan was to keep looking further out, measuring distant galaxies and seeing how fast they were moving. Because the farther away a galaxy is, the further back in time you're seeing it. By comparing those older galaxies to closer, more modern ones, scientists figured they could trace how fast the universe was expanding at different points in time, and see the expected deceleration. You know, just a gentle slowing, like coasting on a hill after a good push. Spoiler, that's not what happened, but you're not quite at the twist yet. First, let's have our quirky moment of the night. In the 1930s, some scientists proposed that maybe the redshifts weren't due to expansion at all, but because light just got tired on the way here. Yes, really. Tired light theory, as if photons were hiking across the universe with no snacks and just gave up a little. It didn't hold up to scrutiny, but honestly, we've all been tired light. You pass now through a conceptual landscape, graphs, data points, 1,000 late-night arguments over beer and bagels. Astronomers in the late 20th century were sharpening their tools, waiting for the right moment. That moment would come in the form of something explosive. But before we get to the fireworks, take a second to appreciate the delicious tension of this era in science. Everyone thought they knew where the universe was heading. Slowing expansion, gravity pulling the reins, predictable, reasonable, almost tidy. The idea that the expansion might be speeding up? Laughable. And yet, as you hover here in this dark sea of assumptions, galaxies still drift apart. Space still expands, quietly, persistently, unbothered by our calculations. Because gravity, for all her power, wasn't the only force in the room. There was something else. A quiet force hiding in the background. Not a bang, not a push, just a nudge, a stretch, a whisper through space-time. And soon someone would find it by accident, staring into the remains of ancient explosions that lit up the darkness billions of years ago. but for now float here in this moment of cosmic certainty. The kind that always comes before the floor falls out from under you. You're gliding now through a velvety darkness, deeper into the cosmos and further back in time. The light out here is thin and strange, like it's travelled too far and seen too much. You coast quietly toward a series of tiny flickering pinpricks. Not stars, but something more dramatic. You're about to witness the universe's fireworks show. These are Type 1a supernova, and they're not here to mess around. Each one is a star's last over-the-top performance. No graceful fade into a red giant, no slow dimming into a white dwarf. These stars go full drama, blowing themselves to pieces in a cosmic tantrum so bright they can outshine their entire host galaxy for weeks. And this is where things take a turn. You slip behind the eyepiece of a telescope in the early 1990s. The lab is cluttered. Coffee cups, sticky notes, tension. Somewhere in the data, something's not adding up. Two teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, are scouring the skies for distant Type Ia supernovae. Why? Because they're not just beautiful, they're useful. You see, these supernovae always explode in the same way, like galactic lighthouses with standardized bulbs. That consistency makes them standard candles, objects so reliably bright, you can figure out how far away they are just by measuring how dim they appear. If you know what a 100-watt bulb looks like up close, you can tell how far away one is by how faint it seems across the room, or, in this case, across the universe. So the idea was simple. Measure the distance to far-off supernovae, compare that with their redshift, and build a map of how fast the universe was expanding at different points in time. The expected result? A nice curve showing the expansion slowing down, gravity doing its job, but that's not what they found. You hover now over the data. It's quiet in the observatory until someone mutters a confused "huh." That tiny word is the sound of the universe refusing to cooperate. Because those supernovae? They were dimmer than expected. Not by much. Just enough to whisper a message that no one wanted to hear. They're farther away than they should be, which meant the universe wasn't slowing down. It was speeding up. You might expect the astronomers to celebrate. Champagne, fireworks, Nobel Prizes. But in that moment, what they felt was dread, confusion, like spotting a crack in your ceiling that's growing just a little too fast. Historians still argue whether the teams realised immediately how big this was. But by the time their results were published in 1998, the message was loud and clear. Cosmic acceleration was real. The universe wasn't just stretching, it was racing apart. This was the kind of result that gets double-checked, triple-checked, sacrificed to the data gods, and then reluctantly accepted while someone mutters, "I hope we're wrong." Because if the universe is accelerating, something must be pushing it. And that's where the mystery deepens. You drift closer to one of those supernovae now. A white dwarf, part of a binary system, has slowly siphoned material off its companion star. A cosmic vampire. When it crosses a critical mass, about 1.4 times the mass of the Sun, it destabilizes, collapses, and then, boom. In less than a second, the white dwarf tears itself apart, releasing more energy than our Sun will emit in its entire 10 billion-year lifetime. That light races across the universe, gets redshifted, stretched by expanding space, and eventually lands in a telescope on Earth. And what it says is, something's not right. Now, here's your quirky tidbit. One of the reasons Type Ia supernovae are so uniform is because they always explode at roughly the same mass. The Chandrasekhar limit, named after the 19-year-old prodigy who figured it out during a sea voyage in 1930. That's right. The physics behind these explosions was partially worked out by a teenager on a boat. What were you doing at 19? Back to the big picture. The data piles up, dozens of supernovae, then hundreds, all saying the same thing. The farther back you look, the slower the expansion used to be. Not because gravity is catching up, but because some mysterious force is speeding things up now. They called it dark energy, mostly because no one had a better name. Dark because we can't see it. Energy because, well, it seems to have some. A sort of negative pressure pushing space apart. But don't get too excited. The naming didn't come with an explanation. It was more like pinning a label on a ghost and pretending that counts as science. Still, it changed everything. You drift now through conference halls and scientific journals as cosmologists scramble to update their models. That tidy trio of options, Big Crunch, Flat Universe, Open Universe, tossed in the bin. because now there's a new scenario, one where expansion accelerates forever. And the implications? Oof. In the far, far future, galaxies will move beyond the cosmic horizon. Their light will never reach us again. The sky will go dark, star by star, galaxy by galaxy, until eventually the only thing visible from Earth will be our own lonely corner of space, like being trapped in a room that keeps getting bigger. But everyone else left ages ago. You linger here for a moment, letting the cold silence of that thought settle. This is where we first began to realize that the universe isn't just big, it's getting away from us, faster and faster, pushed by a force we can't see, can't touch, and don't remotely understand. And just to twist the knife, this discovery won the 2011 Nobel Prize in Physics. Not for figuring out what dark energy is, just for proving it probably exists. The mystery is so large that just not being wrong gets you a medal. So the next time someone tells you the universe makes sense, just smile politely and whisper, "Type I a supernovae say otherwise." You're drifting now in silence, suspended in the pause between one cosmic breath and the next. The light out here is dimmer, not just because you're floating farther into space, but because the very fabric around you is stretching faster and faster. You feel it in your bones, even if you can't quite explain it. The galaxies you passed a moment ago are already farther away. The space between you and them has grown, not because anyone's moving, but because space itself is being pulled open like taffy warmed too long under the sun. And that's the part that broke everyone's brain in 1998. The idea that the universe is expanding, that was fine. A little shocking maybe, but people got used to it. Even Einstein eventually admitted the cosmos might not be fixed in place after all. But accelerating expansion, that was the real twist. It was like being told your car isn't just rolling downhill, it's sprouting rocket boosters and picking up speed for no reason. You coast past a simulation screen now, watching as data points from distant Type Ia supernovae spiral and clump into that unmistakable curve, a rate of expansion that increases over time. What began as a smooth ride away from the Big Bang is now turning into a cosmic joyride with no brakes. This wasn't what anyone expected. Gravity should have slowed everything down. The more mass in the universe, the stronger its gravitational grip. But instead, you're seeing the opposite. Space is expanding faster the further you go, the math doesn't lie. And so, reluctantly, cosmologists opened the door to the weirdest house on the street. They called it dark energy, not because it's evil, though it's a little rude, but because it doesn't shine, reflect, or interact with light in any detectable way. It's just there, doing its thing, quiet, relentless. By this point in the journey, you're probably wondering, what exactly is this force? And the answer is, we don't know. We really don't. It's not made of particles, at least none we can detect. It's not a wave, a field, or even a substance in the traditional sense. It has no flavour, no texture, and quite tragically, no merchandise. It's simply a placeholder, a symbol we've stuck in our equations, the x in the cosmic algebra problem. And yet this unknown thing accounts for nearly 70% of the total energy content of the universe. Let that sink in for a moment. Almost 3/4 of everything is something we don't understand. It doesn't clump like matter. It doesn't pull like gravity. It pushes, gently, persistently, like someone turning the dial on the universe's expansion speed when no one's looking. You hover now above the graphs drawn by the two competing teams in the late 90s, Perlmutter's and Schmidt's. They were trying to map the deceleration of the universe. Instead, both teams, using totally different supernovae, found the same jaw-dropping conclusion: acceleration. Space was getting roomier, faster than before. The results were so unexpected that some scientists initially suspected an error, or a bad batch of exploding stars. Maybe some cosmic prankster had rearranged the data while they weren't looking. Historians still argue whether anyone celebrated in the traditional sense. There were no balloons, no ticker tape, just a lot of pacing, rechecking, and eventually the quiet resignation that physics had just gotten harder. So, what happens when the universe is accelerating? You drift now toward the event horizon of possibility. Galaxies that are currently visible will someday vanish beyond our reach. The faster the universe expands, the less of it we'll be able to observe. There's a limit, an invisible edge, beyond which light simply can't reach us anymore. It's not blocked or hidden, it's just too far gone, like someone turning off the stars one by one. Eventually, the only galaxies left in our sky will be the ones gravitationally bound to us, like the Andromeda Galaxy, which is actually headed our way. Someday far in the future, it will collide with the Milky Way, and they'll merge into a new, more massive galaxy, Milkdromeda. Yes, that's the unofficial name, and no, we're not taking votes. But after that merger, once the fireworks settle and the universe keeps expanding, everything else will fade, galaxies will disappear, signals will vanish, and astronomers of the far future, assuming they still exist, might see only their own galaxy and assume the universe is static, eternal, and lonely. A cosmic irony. The more the universe accelerates, the less of it we'll know. Here's your quirky little tidbit. In the early 2000s, some physicists joked that dark energy might be a kind of anti-gravity latte. Smooth, widespread, and strangely addictive to theoretical physicists who can't explain it. There were even April Fool's papers about vacuum espresso and entropy foam. Because when the universe starts speeding away from you, sometimes the only thing left to do is make a joke and keep observing. You coast past satellite observatories, like WMAP and Planck, that were launched to map the early universe's faint glow and decode the fingerprint of this mysterious acceleration. And while the data confirmed what we feared, it offered no comfort, no explanation, just a clearer, sharper view of the mystery. You also glide by theoretical physicists, hunched over whiteboards covered in equations, attempting to balance a universe that's pushing itself apart. Some toy with quantum fields, others try modifying gravity, and a few just take long walks and mutter to themselves. Because again, we know what dark energy does. It accelerates expansion, but we don't know what it is. Some call it a property of space itself, others say it's a dynamic field like weather in space-time, and a few dare to suggest it's an illusion, something that only looks like acceleration because we haven't grasped the deeper geometry of the cosmos. But none of these are proven, none of them are complete. Historians still argue whether dark energy is a real physical entity, or simply the universe's way of telling us we're missing something fundamental, something embarrassingly basic. So now you float, not just between galaxies, but between ideas, between the physics we think we know and the reality that keeps expanding without asking our permission. The universe is accelerating, that's the one thing we're sure of. What comes next? Well, that depends on just how far dark energy is willing to go. You're weightless again, still gliding through a universe that won't stop running from itself. The stars are fewer now, farther apart, like someone hit the slow motion button on reality, and everything just keeps sliding outward in quiet defiance of gravity's old rules. You're drifting through invisible currents, past the galaxies being gently shoved by a force with no face and no explanation. It's subtle, yes, but it's everywhere. It touches every cubic centimetre of space, from the emptiest voids between galaxies to the cluttered neighbourhood around Earth. This is the force that we, somewhat lazily, somewhat poetically, name dark energy. And tonight, you get to watch the moment it officially entered the scientific vocabulary. The scene is a quiet lecture hall, early 2000s. There's no drama, no thunderclaps, no celestial music cue. Just a bunch of astrophysicists nervously agreeing that this accelerating expansion thing isn't going away. It wasn't a data error. It wasn't bad math. Something real was happening. And if they were going to talk about it without their papers getting laughed out of peer review, it needed a name. So, dark energy. It wasn't the most elegant label, but it stuck. Dark because it's invisible. Energy because, well, it has to be something that's pushing. Something with presence, even if it's not tangible. A kind of negative pressure that acts on the vacuum of space itself. You watch the terms start spreading, across journal articles, then textbooks, then science documentaries hosted by people with soothing voices and suspiciously good hair. Dark energy becomes a placeholder for a great cosmic mystery. It makes headlines. It earns grants. It becomes the thing scientists say when they want to sound impressive at dinner parties. And yet, it tells us nothing about what it is. Naming it dark energy is like naming your headache brain ouch and pretending that counts as a diagnosis. Here's your quirky historical tidbit of the night. When Einstein first added his cosmological constant, a term we'll revisit in a moment, it was essentially the same thing as dark energy. He just didn't know it yet. His version was meant to hold the universe in place, not push it apart. But once we realised the universe was expanding, the term was scrapped, only to be dragged back from obscurity decades later and rebranded as cutting edge. Science can be fashionably circular like that. So now the term is out there, dark energy, and with it comes the need to quantify it. You hover near a chalkboard scrawled with equations, where cosmologists start adjusting the Friedmann equations, the mathematical backbone of modern cosmology. They need a new variable, a pressure term, something to account for the repulsive force accelerating expansion. And right there, sneaky, humble, quietly revolutionary, is a value known as W, just W, the equation of state parameter for dark energy. If W equals -1, you get a cosmological constant, a uniform, constant energy density filling space. If W is anything else, it opens the door to all kinds of wilder ideas, phantom energy, quintessence, K-essence, and probably some theories made up by grad students who needed a thesis topic at 2 a.m. But at this point we're still in the early 2000s. The data all points to W being very close to -1, which means dark energy might just be a constant, no change, no fluctuation, just a feature of the universe baked into its fabric like raisins in cosmic bread. This possibility sends everyone scrambling back to Einstein's equations. Turns out the old man may have been onto something after all. You coast into a theoretical physics seminar where someone quietly proposes, what if the cosmological constant isn't a blunder, but the answer? Historians still argue whether Einstein would have felt vindicated or just annoyed that we circled back to his discarded math, like cats returning to a broken box. But here's the rub. If dark energy really is constant, then the future of the universe is already written. No surprises, no twists, just slow, endless acceleration forever. You're now passing between two clusters of galaxies. Normally gravity would be pulling them toward each other. But with dark energy in the mix, that pull gets overpowered. You can almost feel the cosmic tension, gravity trying to stitch the universe together, dark energy gently snipping the threads. And this brings us to a philosophical pit stop, because when you name something, you start to act like you understand it. But dark energy remains stubbornly slippery. Is it a substance, a property, a glitch in the cosmic code? A few brave souls even suggest we're misinterpreting the data entirely. That maybe we're seeing expansion not because something's pushing us, but because our assumptions about the shape and age of the universe are wrong. That's the thing about science at the edge. Every answer spawns 5 new questions and at least one really long Reddit thread. You float into a meeting of the Dark Energy Task Force. Yes, that was a real thing formed in the early 2000s to help coordinate US research efforts. The name makes it sound like they're fighting ghost energy with high-tech gadgets. But really, it's just a bunch of very tired people in beige conference rooms trying to design better surveys and space missions. The result? Massive sky mapping projects like DES, Dark Energy Survey, Euclid, and the Vera Rubin Observatory, all aiming to map the expansion of the universe in finer detail and pin down dark energy's behavior across cosmic time. If it changes even a little, the implications could rewrite everything. And now, a quick quirky sidebar. The nickname Dark Energy has been widely misused in sci-fi. In one popular video game, it's treated like a power source for weapons. In another, it's a dangerous force to be weaponized or harnessed. In reality, it's more like an annoying breeze you can't stop. Not deadly, not flashy, just slowly unzipping the universe while we watch in our pajamas. So here you are again, drifting between galaxies surrounded by something that fills space but doesn't act like anything we know. No glow, no weight. Just a quiet push that gets stronger over time. Naming it was just the first step. Understanding it? Well, we're still working on that. You're floating now through the hazy borderlands between classical physics and modern cosmology, a sort of theoretical twilight zone where even the most confident equations start to look a little twitchy. And there, dusted off and glowing faintly with embarrassment, is a very old idea that just won't stay dead. You're staring at Einstein's cosmological constant. Once tossed aside as the biggest blunder of Einstein's career, this quiet little term has crept back into relevance like a forgotten actor suddenly trending again. Its return is awkward but timely, because as it turns out, this fudged bit of math might be the best explanation we have for dark energy. Let's rewind for a moment. Back in 1917, Einstein had just formulated his general theory of relativity, a gorgeous set of equations describing how matter bends space-time. But there was a problem. His equations didn't allow for a static universe. They predicted that space should either be expanding or contracting, which at the time seemed wrong. The night sky looked pretty stable, so like a man trying to balance a lopsided cake, Einstein added a term to his equations, the cosmological constant, usually written as lambda. This extra force acted as a kind of anti-gravity, perfectly balanced to keep the universe from collapsing or flying apart. But then Hubble came along, showed that the universe was expanding after all, and Einstein reportedly called his lambda trick the greatest blunder of my life. Historians still argue whether he actually said that, or if it was a later embellishment by physicists who liked a good comeback story. Still, lambda was quietly shelved, until the late 1990s, when astronomers noticed that expansion wasn't just happening, it was accelerating. And suddenly, that old cosmological constant didn't seem like such a bad idea after all. The exact same term Einstein had used to stabilize the universe could now be reinterpreted as the thing causing it to speed up. So what exactly is the cosmological constant? Well, that's complicated. You're floating now inside the equations themselves, letting the variables swirl around you like fireflies. Lambda represents a constant energy density that fills all of space, like a built-in pressure of the vacuum, exerting a quiet outward push. It's not a substance. It's not even energy in the way we understand from batteries or sunlight. It's more like a feature of space itself. If you take all the stuff out of the universe, all the stars, all the gas, all the dust, and even all the dark matter, you'd still be left with this gentle, persistent push, an energy intrinsic to nothingness, which of course is completely bonkers. You drift into the minds of quantum physicists now, slightly more stressed than the average cosmologist, with more coffee mugs per capita, and you find them asking, where does this constant come from? And here comes the plot twist. According to quantum field theory, empty space isn't really empty. It seethes with fluctuations, popping virtual particles in and out of existence in a constant quantum froth. These blips of energy, theoretically, should contribute to the energy density of the vacuum. In other words, they should be the cosmological constant. But when physicists actually try to calculate this, the predicted value is around 10 to the power of 120 times larger than what we observe. That's a 1 followed by 120 zeros. The biggest discrepancy between theory and observation in the history of science. It's like ordering a coffee and getting a small black hole instead. This little disaster is called the cosmological constant problem, and it's still unresolved. Historians and current physicists still argue whether this means we're missing a fundamental piece of the puzzle, or if we're just doing the math wrong in the most magnificent way imaginable. Meanwhile, lambda keeps showing up in all the right places. When we model the early universe, lambda fits. When we look at the cosmic microwave background, yep, still there. When we simulate galaxy formation, you guessed it. So for now, lambda has been quietly reinstated in the standard model of cosmology. That model even has a charming name, lambda CDM. The lambda for the cosmological constant, dark energy, and the CDM for cold dark matter. It's not perfect. It leaves dozens of questions unanswered, but it's the best thing we've got. Here's your quirky fringe tidbit for the night. Some theories suggest that lambda might not be constant after all, that it might decay over time, or vary in strength across different regions of space, or flip signs and eventually reverse, turning acceleration into contraction. These are fringe ideas, but in cosmology, fringe sometimes means check back in 10 years. You float now beside a simulated timeline of the universe, watching as dark energy slowly takes over. At first, matter ruled. Galaxies clumped together under gravity, stars formed, black holes feasted. But as space expanded, matter thinned out and dark energy, constant and unchanging, began to dominate. Now, in this current era, dark energy accounts for nearly 70% of everything. Matter is a fading minority. The cosmological constant won. So what does this mean for the far future? Unless something changes, unless that constant turns out to be not so constant, acceleration will continue. Galaxies will drift beyond our view. The night sky will go dark. Eventually, even the cosmic background radiation will be stretched beyond detectability. And yet, there's a strange comfort to it, a kind of slow fade instead of a dramatic bang. The universe becomes quieter, more still. a whispering stretch into eternity. But still, no one knows why it's happening, why the cosmological constant has the value it does, why it even exists. The math allows it, the observations demand it, but the meaning? That's still up for debate. You float then, in this strange space between elegance and confusion, between Einstein's accidental foresight and our current bewilderment, between a symbol, lambda, and a force that may decide the fate of everything. It's not often that an equation's mistake becomes its best feature, and it's not often the universe keeps expanding and just because it can. You're floating now in a space that's not really empty, not truly. It looks like nothing, feels like nothing. But if you sit quietly and listen, long enough and carefully enough, you start to notice the flickers, little pops, gentle jitters, like the universe is fidgeting in its seat. This is what physicists call the quantum vacuum, the place where nothing is suspiciously busy. And tonight, you're going to get uncomfortably close to one of the strangest possibilities in all of science, that the force pulling the universe apart, that mysterious dark energy, might just be the result of these quantum whispers. Welcome to the world of vacuum energy, a kind of something that lives inside what we used to call nothing. You hover inside a region of empty space, far from any galaxy or star. It's the kind of silence that should be absolute. But according to quantum field theory, that silence is a lie. Even in the coldest, most vacant corner of the universe, there's activity. Little fluctuations, virtual particles blinking in and out of existence like fireflies playing quantum peekaboo. They appear, they disappear, they have no long-term presence, and yet they exist, however briefly. And if that sounds like nonsense, well, you're in excellent company. Einstein didn't like it either, but over time the quantum vacuum went from a strange prediction to a testable part of reality. Experiments like the Casimir effect show that even two uncharged metal plates placed close together in a vacuum will feel a measurable force between them, not because of some invisible field, but because the vacuum itself has energy. The plates restrict the kinds of virtual particles that can exist between them, creating a pressure imbalance. Voila, movement from nothing. You drift past a laboratory now, the plates set up with absurd precision, lasers watching every micron, and all because empty space isn't. So what does this have to do with dark energy? Well, vacuum energy acts a lot like what we observe dark energy doing. It has a uniform density, it doesn't clump or dilute with time, it fills space evenly, no matter where you go. If vacuum energy really is responsible for the universe's accelerating expansion, then we've had the answer this whole time. It's just been quietly humming in the background like cosmic refrigerator noise. There's just one little problem. When we calculate how much vacuum energy there should be, based on known quantum fields, particle physics, and all the clever math, we get a number that's catastrophically wrong. Off by a factor of 10 to the power of 120. That's one followed by 120 zeros. Let that sit with you for a second. That's not just a rounding error, that's a full-blown cosmological crisis. If the vacuum had that much energy, space would be expanding so violently that galaxies, stars, and even atoms could never form. You wouldn't be here. Nothing would. So now you're floating in a deeply unsettling paradox. Vacuum energy might explain dark energy, but it can't explain it in the numbers we currently have. Either something is cancelling most of it out, or we've misunderstood something fundamental about both quantum mechanics and gravity. Historians still argue whether this mismatch is the biggest unsolved problem in physics today. Some call it the worst prediction ever made in science. Others politely refer to it as an opportunity for theoretical growth. You know, the way you describe a sinkhole opening under your house. But let's not get too lost in despair. You glide through a landscape of competing theories, each trying to tame this vacuum chaos. Some physicists propose a mysterious balancing mechanism, a sort of cosmic subtraction, where positive and negative energies cancel out, leaving just a small leftover force that acts like dark energy. Others dive into the speculative depths of supersymmetry, a theory where every particle has a partner, and these pairs conveniently cancel each other's vacuum contributions. Neat, elegant, unfortunately, still unproven. There's also the idea of zero-point energy, a concept that suggests even the lowest energy state of a quantum field has residual energy. It's the kind of thing that gave rise to all those sci-fi tropes about limitless energy pulled from the vacuum. In fiction, it powers alien starships and time portals. In reality, It might be what's slowly tearing the universe apart. And here's your quirky little rabbit hole for tonight. In the 1970s, a few very enthusiastic inventors tried to build zero-point energy machines to power cars and homes. Most of them were promptly debunked, of course, but every few years someone pops back up on YouTube claiming they've harnessed the power of the vacuum. Spoiler, they haven't. But we admire the ambition. Back in reality, you now coast toward the quantum scale, smaller than atoms, smaller than protons, where particles are more like suggestions than objects, and uncertainty reigns. It's here that vacuum energy supposedly resides, woven into the jittery fabric of existence. And somehow, this jittery nothingness is governing the larger scale behavior of the entire cosmos. That's the bizarre beauty of it. The same quantum fields that make electrons wobble or give particles mass may also be pushing galaxies away from each other at increasing speeds. The very small, ruling the very large. It's like finding out ants are responsible for continental drift. You drift for a moment in that realization. All of space, all the vast starless voids, filled with this invisible energy, always there, always working, and yet so incredibly weak, just strong enough to shape the fate of everything without ever being felt directly. If vacuum energy really is dark energy, then that means the expansion of the universe is not driven by some exotic new particle or field. It's a property of reality itself, not something in space, but something of space. And if that doesn't make your eyebrows levitate, nothing will. But there's still resistance. There are physicists who argue this can't be the full story, that dark energy might change over time, that it's not a constant, that it might one day vanish or spike or flip, hurling the cosmos into collapse. Vacuum energy might just be the calm before a weirder storm, so you keep floating, quiet, thoughtful, surrounded by emptiness that isn't really empty, space that is never truly still. And you begin to understand, maybe nothing isn't such a simple idea after all. In fact, it might be the most powerful force we've ever known. You drift now through the distant edges of imagination, where mathematics stretches its fingers toward possible futures, and none of them feel especially cozy. The universe hums beneath you, quietly expanding faster than before with no plans to stop. You glance around at the galaxies, elegant spirals, glowing ovals, islands of light. They feel eternal, don't they? But what if we told you they aren't? What if the universe doesn't just expand forever, gently and coldly? What if that expansion accelerates so drastically, so violently, that it eventually tears the very fabric of reality apart? Atoms, molecules, stars, even the strings of space-time themselves, ripped into silence. Welcome to the most unsettling possibility in all of cosmology, the Big Rip. No, it's not the sequel to the Big Bang, although it does have the same sense of finality. The Big Rip is the cosmic version of going a little too hard at yoga and accidentally dislocating the universe. It's what happens if dark energy is not constant, not well behaved, and not interested in playing nice with gravity. You drift now through a hypothetical timeline. It begins like today, peaceful, galaxies coasting away from each other, dark energy doing its slow push thing. But over time, something changes. Dark energy strengthens. Maybe its density increases. Maybe W, that little equation of state parameter we met earlier, dips below -1. That value is the danger zone, the line between creepy expansion and catastrophic expansion. Cosmologists call it phantom energy, and despite the spooky name, it's not supernatural. It's just regular dark energy turned up to 11. Instead of staying constant as the universe expands, it grows. More space, more energy, faster expansion, more space. You can see where this is going. This creates a terrifying feedback loop. The more space expands, the more phantom energy floods in. The more phantom energy there is, the more violently it pushes space apart. Eventually, not even gravity can hold things together. First, galaxy clusters lose their grip. Then galaxies themselves begin to disintegrate. You float by the Milky Way as its arms unravel like loose threads, stars flying off into the void. The Andromeda merger never happens, no Milkdrometer for you. Then, solar systems fall apart. The gravitational pull of stars can no longer keep planets in orbit. Earth, if it still exists, is flung into the darkness like a skipped stone, trailing confused satellites. Eventually, even the bonds holding planets together are overwhelmed. You pass a rocky world splitting open like a dried-out fruit. Then comes the truly intimate destruction, atoms themselves. The electromagnetic force that binds electrons to nuclei gives out. Molecules dissolve, chemistry ends, and in the final seconds, yes, seconds, space itself is shredded. The distances between subatomic particles go infinite. Quarks, gluons, space-time, all torn from each other in a last frenzied expansion. The universe ends, not with a bang, not with a whimper, but with a scream of stretching geometry. Historians still argue whether the Big Rip is a real possibility or just a fun mathematical nightmare. It depends entirely on the nature of dark energy, and whether its strength increases over time. If W stays firmly at -1, no problem. If it dips below, start writing your cosmic will. Current observations suggest W is very close to -1, maybe just below, maybe not. The error bars are small, but not small enough to rule out this possibility. So, we keep watching, we keep measuring. We hope the universe isn't secretly plotting its own full-body disassembly. And here's your quirky tidbit for tonight. If the Big Rip happens, and you happen to be near the final phase, say, within the last few years of the universe, you'd be able to see galaxies vanish. Not just redshift and fade, but disappear, right before your eyes, as the speed of expansion drags them beyond causal contact. That's like watching the sky go out, one light at a time, until all that remains is a flickering personal bubble that collapses with you. You might be thinking, surely there's a way to stop this. Well, no. If phantom energy exists, it's built into the vacuum itself. You can't turn it off. There's no off switch for reality stretching itself into shreds. All you can do is watch, and maybe whisper a quiet "oops" as your molecules part ways. But let's not spiral just yet. The Big Rip is still speculative. It depends on parameters we haven't pinned down, and so far, the data hints that we probably aren't on the path to catastrophic unzipping. Still, the idea is a powerful reminder. The future of the universe depends entirely on the nature of something we don't understand. If dark energy changes over time, if it's not a constant but a field, then all bets are off. It could decay, it could grow, it could morph into something else entirely. That's what makes cosmology feel like speculative fiction, except it's math doing the world building, and the plot twists don't care how we feel about them. You float now in a moment of eerie calm just imagining it. The horizon shrinking, galaxies flying apart, the soundless unravelling of structure. It's peaceful, chilling, beautiful in a kind of minimalist apocalypse way, and yet, there's a strange comfort in knowing we'll never see it. If the Big Rip does happen, it's likely trillions of years from now, long after the last star flickers out, long after the last galaxy fades, long after even the most stubborn black holes have evaporated. It's a problem for the universe, not for you. Still, you tuck the thought away like a spooky bedtime story and drift gently on. Because even if the cosmos isn't planning a full-body rip in the future, it's still stretching, and it still refuses to tell us why. You're floating now through calmer currents, moving away from the catastrophic visions of universal unravelling. The stars still shine around you, distant, quiet, patient. For now, the universe isn't ripping apart at the seams. It's expanding, yes, but with a kind of gentle persistence, like it's in no particular rush, but definitely not planning to stop. So maybe it's not a violent doom waiting in the future. Maybe dark energy isn't a ticking time bomb. Maybe it's something more graceful. And tonight you hover in the presence of a gentler possibility, quintessence. Now the name alone sounds like it was pulled from a fantasy novel, something a wizard might summon from a crystal sphere, but it's very real, at least mathematically. Quintessence is one of the most intriguing alternative explanations for dark energy, and unlike the cosmological constant, it's dynamic. It can change over time, it can roll, it can fluctuate, it might even turn off one day. You glide now through a universe shaped not by a static vacuum pressure, but by a field, much like the one that gave us the Higgs boson. Quintessence isn't a thing in the usual sense. It's a field that permeates all space like an invisible fog of intent. It carries energy, but not uniformly. It evolves, and if it exists, it could be responsible for the accelerated expansion of the universe, but with a personality more complex than the blank, unchanging push of the cosmological constant. So how does this magical sounding field work? Well, like any good theoretical entity, it has potential energy, much like a ball sitting on a hill. The shape of the hill, the potential, determines how the field behaves. If the slope is steep, the field rolls quickly. If it's shallow, the field rolls slowly. And in the case of quintessence, a slowly rolling field can produce a negative pressure, enough to accelerate the universe's expansion. The trick is tuning the potential just right. Too steep and you get behavior that doesn't match observations. Too flat, and you basically reinvent the cosmological constant in a lab coat. You drift into a visualization now, space as a smooth sea, and quintessence as a current moving beneath it. Not a constant swell, but a slowly changing wave that shifts the entire ocean over time. Historians still argue whether quintessence was proposed to solve real theoretical gaps, or just because physicists were bored with lambda and wanted a fancier mystery. But it's gained real traction, especially among those who are deeply allergic to fine-tuning problems. Because here's the issue. The cosmological constant requires an absurd amount of fine-tuning. The vacuum energy from quantum physics is huge, but the actual observed dark energy is tiny. Why? Why does the math demand a cosmic subtraction of 120 decimal places, leaving behind just enough energy to accelerate the universe, but not enough to blow it apart? Quintessence offers a way out. If dark energy is a field that slowly evolves, maybe we're just currently living in a phase of gentle acceleration. No absurd precision required, just a universe passing through a chapter in its ongoing story. And here's your quirky tidbit. The term quintessence actually comes from ancient Greek philosophy. The fifth element, beyond earth, air, fire, and water. They believed it filled the heavens, a perfect celestial substance. So, in a way, modern physics accidentally looped back and gave the ancients a poetic high five. Good job, Plato. You were off by a couple thousand years and a few equations, but the vibe was there. Back in the realm of data, scientists are actively hunting for signs of quintessence. If it's real, its effects should be subtle, but detectable. Maybe small changes in the rate of expansion over cosmic time. Maybe tiny imprints in the cosmic microwave background. Maybe whispers in the distribution of galaxies that say, "Hey, I'm not a constant. I'm just vibing." You float past future missions like Euclid or the Nancy Grace Roman Space Telescope, designed to track the expansion of the universe with absurd precision. These missions are trying to catch the tiniest drift in the behavior of dark energy over billions of years. If they detect it, that would be a major hint that quintessence is real, that dark energy has moods. Now the catch. Quintessence also brings its own baggage. It requires extra assumptions, more parameters, more fine-tuning of a different flavour. And as always, until we detect a direct signature, it remains a speculative layer built on an already mysterious cake. But it opens up more possibilities. Like what? Well, for starters, quintessence can turn off. Unlike a constant cosmological pressure that persists forever, a field can fade. It can settle into a minimum. It can decay into something else. And that means the current acceleration of the universe might not be permanent. You might be floating through a temporary phase, a cosmic growth spurt. Eventually, the universe could return to slow expansion, or even collapse. That flexibility is one of the field's most tantalizing features, and it's most chilling. Because if dark energy is changing, then the universe's fate isn't written in stone, it's in flux. We don't live in a neat geometric reality with clean end chapters. We live in an evolving system full of surprises. Imagine that. In a few billion years, dark energy starts to fade. Gravity regains the upper hand. Galaxies start pulling back together. The universe slows, then contracts, maybe even ends in a big crunch, a reversal of the Big Bang where everything collapses into a hot, dense point. Or perhaps dark energy flips polarity, becoming attractive instead of repulsive. That's a recipe for chaos, but hey, the universe likes a little drama. And here's where the scholarly debate turns theatrical. Some theorists claim quintessence is more natural than a cosmological constant. Others argue it's just lambda wearing a fancy wig. And a few, bless them, are still arguing whether any of this even matters if we can't measure W to the 5th decimal place. But that's the fun of it, isn't it? Theorizing at the edge of knowledge, staring into the dark and imagining all the invisible forces that might be shaping our fate. So, You float again, gently, listening for the field. The quintessence, if it's there, is whispering across the stars. Not a shout, not a rip, just a presence, a slow drift, a subtle pressure from a time before stars. And if it's real, well, maybe the universe isn't coasting to an icy death or ripping apart at the seams. Maybe it's just rolling softly toward whatever comes next. You're drifting now through warmth. Well, ancient warmth. Long cooled, but still echoing faintly across all of space. You're gliding through the cosmic microwave background, or CMB if you're in a hurry. It's the afterglow of the Big Bang still glowing ever so slightly, like the embers of a fire that went out almost 14 billion years ago. It wraps around you like a soft, invisible fog, smooth, uniform but with tiny imperfections, barely there ripples in temperature, variations of just millionths of a degree. And yet, those baby bumps are the seeds of everything. Every star, every galaxy, every structure in the universe started out as a little wrinkle in this cosmic blanket. And yes, believe it or not, this dusty glow from the early universe may hold the key to understanding dark energy. You might be wondering, how can ancient light tell us about something that didn't become noticeable until billions of years later? A fair question. But remember, light is a gossip. It travels, it carries stories, and it never forgets. Especially not when it's been stretched across time and space by the expansion of the universe itself. The CMB was first detected in 1965 by accident. Two radio astronomers, Arno Penzias and Robert Wilson, were trying to calibrate an antenna, and couldn't figure out why they kept hearing a persistent hum. No matter what direction they pointed it, no matter how many pigeons they shooed out of the equipment, yes, that really happened. The hum was everywhere. What they'd stumbled upon was the oldest light in the universe, a snapshot of the cosmos just 380,000 years after the Big Bang, when the universe finally cooled enough for photons to travel freely, no longer constantly bouncing off charged particles like drunk bees at a rave. And here's your historical fact of the night. The existence of this glow had been predicted almost 2 decades earlier by theorists, but no one believed it until it was accidentally measured. The Nobel Committee loved that. Anyway, you're drifting through this ancient glow now, letting its patterns wash over you. It's like looking at a baby picture of the universe, blurry, colourful, a little asymmetrical, but critical. Because those tiny fluctuations, the ones that would eventually become galaxies, also encode something deeper, information about the universe's geometry, composition, and expansion history. You float beside one of the satellites that map this glow in exquisite detail, WMAP, followed later by Planck. These spacecraft turned the whole sky into data, producing maps that look like psychedelic egg yolks but are actually profound portraits of space-time itself. And embedded in those maps are clues about dark energy. How? Well, let's talk angles. One of the key things scientists can extract from the CMB is the angular size of those tiny fluctuations. Depending on the geometry of the universe, flat, curved, or saddle-shaped, the apparent size of those ripples changes. And surprise, surprise, they look just right for a flat universe. Flat geometry means that on large scales, Euclidean geometry applies. Parallel lines don't meet. Triangles add up to 180 degrees, and your Pythagorean theorem still works after 13.8 billion years. Now here's the thing, a flat universe requires a very specific amount of total energy density. Add up all the matter, radiation, dark matter, and you're still short. In fact, you're short by about 70%. That missing piece? You guessed it, dark energy. The CMB, in its soft, whispery glow, is basically shouting at us. Hey, there's a chunk of the universe you're not seeing, and it's making space expand weirdly. So while the CMB doesn't show dark energy directly, it reveals its presence through math, by balancing the cosmic books. Without dark energy, the universe would appear curved. Instead, it's astonishingly flat. Which only makes sense if something else, something unseeable, is filling that final 70% of the energy budget. Historians still argue whether this counts as proof of dark energy or just another nudge. But in combination with the supernova data and large-scale structure observations, it forms a compelling triangle. Multiple lines of evidence pointing to the same unsettling truth. Now for your quirky tidbit, the Planck satellite measured the CMB so precisely that it detected gravitational lensing of the background light, meaning even the way the glow bends tells us about the stuff sitting between us and the edge of the observable universe. Dark matter, galaxies, and yes, dark energy. Lensing smudges the patterns just enough to whisper, there's something else here. And it's changing the shape of space. You float through these imprints now. They look like ripples in water, but they're encoded in microwaves, light stretched by billions of years of expansion. Light that passed through the entire cosmic web, touching every cluster, slipping past every star, distorted ever so slightly by the invisible scaffolding of the cosmos. And that scaffolding, the shape of it, the speed it formed, how quickly galaxies pulled together, isn't quite what we'd expect without dark energy. Everything fits better with it than without it. It's the missing puzzle piece that makes the cosmic microwave background snap into focus. Still, some scientists remain skeptical. They suggest maybe we've misunderstood the early universe, or maybe our measurements have systematic errors, or maybe dark energy isn't needed if some other force, like modified gravity, is tweaking our observations behind the scenes. We'll talk about those theories soon, but for now, you just float in the warmth. This leftover radiation from the beginning of time, once blindingly hot, now cooled to just 2.7 Kelvin, still glowing, still speaking. Every patch of the sky you see tonight is a fossil of that ancient time, and buried in that fossil record is a warning. Expansion is winning, structure is fading, and something invisible is pulling the threads loose. Dark energy doesn't leave fingerprints, but it warps the light from the past. It shapes the largest patterns in the sky, and if you know how to listen, it tells you that the universe has no intention of stopping. You're drifting now through a space that feels like a quiet kitchen just before a cosmic bake-off, where the ingredients are galaxies, the recipes are physics models, and the final dish is the fate of the universe. No pressure. In this section of the journey, you're floating past the theoretical ovens of modern cosmology, watching as scientists line up their best attempts to explain it all. The universe's expansion, its speed, its age, the mysterious push of dark energy. Welcome to what might be called the Great Cosmic Bake-Off, a slow-cooking, high-stakes contest where various cosmological models compete for accuracy, elegance, and that elusive ingredient, truth. You glide gently past the reigning champion first, Lambda CDM, our standard model. You've met it before, Lambda for the cosmological constant, and CDM for cold dark matter. It's like the chocolate chip cookie of cosmology. Widely accepted, relatively simple, and surprisingly robust given how many ingredients we don't understand. Lambda CDM is elegant on the outside, deeply weird on the inside. It assumes three main components: ordinary matter, which makes up about 5%, dark matter, around 25%, and dark energy, about 70%. Add in some early inflation, sprinkle in the cosmic microwave background, and voila, you've got a model that explains nearly every observation we have. It works, it really works, until it doesn't. You float beside a chalkboard crammed with equations and see where things start to crack. The so-called Hubble tension is front and center. Two different ways of measuring the universe's expansion rate yield two different answers. If you look at the early universe using the CMB, you get a number around 67 kilometers per second per megaparsec. But if you look at nearby galaxies and supernova, things that are more recent in cosmic terms, you get something closer to 73. That gap may sound small, but it's statistically significant. It's like baking two cakes with the exact same recipe and oven temperature, and one comes out chocolate and the other comes out, I don't know, lasagna. Something's off. Historians still argue whether this tension means our model is broken, or just needs a few extra ingredients stirred in. Some suggest the data is being misread. Others think new physics is hiding in the oven mitt drawer. So new models begin to emerge, like hopeful contestants on a cooking show. First up, you drift past dynamical dark energy models, fancier versions of the standard recipe where dark energy isn't constant but changes over time. Quintessence is a member of this club, as is K-essence, yes, spelled with a K, because theoretical physicists are bad at branding. These models try to explain the Hubble tension by tweaking the timing. Maybe the expansion ramped up faster than we thought, or started earlier. Then come the early dark energy models, where a temporary burst of dark energy happened long before galaxies formed. Think of it as a flash of microwave in the middle of a slow roast. It might help explain why we see a faster expansion rate today than we expect based on the early universe. These models are clever, but need to be tuned just right to match observations without breaking everything else. You float past these theoretical cookbooks, pages fluttering with differential equations, each more desperate than the last to bake something that fits all the data. And now for tonight's quirky tidbit. One team proposed a model where dark energy comes from a slowly decaying field left over from the early universe that relaxes over time. The nickname? The relaction. Yes, like a cosmic action figure. No, it does not come with accessories. Moving on, you pass through more radical ideas, like modified gravity models, which we'll explore more deeply soon. These bake in changes to Einstein's equations, suggesting we don't need dark energy if we just rewrite the rules of gravity. It's a bold move, like replacing flour with sawdust and hoping no one notices. Occasionally brilliant, often inedible. Other models try to change the geometry of the universe. Maybe space isn't quite as flat as we thought. Maybe the curvature is tiny, but enough to mess with our measurements. You float by a room of cosmologists arguing about this possibility, and if you listen closely you'll hear statistical significance, whispered like a prayer or a curse, depending on who's speaking. Now, a brief intermission in the bake-off. Let's remember that all of these models must pass a brutal taste test. They don't just need to explain the expansion rate, they also have to match observations of the large-scale structure of the universe. The abundance of elements from Big Bang nucleosynthesis. The detailed patterns in the cosmic microwave background. The growth of galaxy clusters over time. Supernova distances and redshifts. If your model flunks even one of these, it gets tossed in the theoretical compost bin. You float now into one of the most visually mesmerizing parts of this journey. Simulations of the universe, rendered with petabytes of data. These are virtual universes, evolved over billions of simulated years. They start with simple physics rules and dark energy parameters, then grow filaments, galaxies, and voids that mirror what we see in telescopes. Tweak the amount or behavior of dark energy, and the whole simulation warps. Clusters grow too fast or too slow. Voids become too large, or structures too clumpy. It's a bit like adjusting the amount of baking powder in a cake. Too much, and you get a science fair volcano. Too little, and it collapses in on itself. You pause to watch a simulation run in fast forward, bright webs of galaxies forming and stretching outward, dark matter halos shimmering like bones beneath the skin, and in the background, quietly, almost politely, dark energy pulling space apart at an ever-steady pace. And here's your gentle reminder. Every one of these models is a guess, an educated guess, yes, with math and evidence. But a guess nonetheless. No one has found the perfect recipe yet. Maybe there isn't one. Maybe the universe is less a baked good and more an experimental stew that never quite stops simmering. So you drift again between models, between constants and rolling fields, between tweaks and rewrites, and you realize that dark energy isn't just a problem, it's a test of imagination, of observation, of our ability to admit that the best current answer might still be wrong. The cosmic bake-off isn't over, and the timer's still ticking. You're drifting now into the dim, shadowy corridors of the cosmos where misunderstandings love to hide. It's quiet here, not the calm of empty space, but the kind of hush that comes when two things get routinely confused for one another, pulled into the same sentence, treated like twins. But tonight, let's clear the air between these two celestial misfits, dark energy and dark matter. Yes, they're both dark. Yes, they both sound ominous. Yes, neither of them has been directly detected, but they are not the same, not even close. In fact, they're doing completely opposite jobs, like cosmic co-workers who don't talk and probably wouldn't get along if they did. So you float now between the two forces that rule most of the universe, dark energy pushing everything apart and dark matter holding things together. It's like you're stuck between an invisible accelerator and an invisible glue gun. Let's meet the elder sibling first, dark matter. You've probably heard its name in hushed sci-fi tones or whispered during late-night physics rants. It's been around in scientific discussion since the 1930s, when Swiss astronomer Fritz Zwicky noticed something weird. Galaxy clusters were spinning too fast, way too fast. There wasn't enough visible mass to account for the speed. By all rights, those galaxies should have flung themselves apart like wet dogs shaking off in slow motion. Zwicky proposed that there was some kind of invisible stuff, He called it dunkle materie, or dark matter, providing extra gravitational heft. At the time, most people politely ignored him. Historians still argue whether that was because of his personality — Zwicky was famously abrasive — or because the idea was just too wild for the era. But decades later, with better telescopes and sharper models, other astronomers confirmed what he saw. Dark matter is everywhere, not in the form of black holes or rogue planets. Those were ruled out pretty quickly, but as a smooth, non-interacting substance. It doesn't emit or reflect light. It doesn't scatter photons, but it has mass, and that means it exerts gravity. You drift now through a dark matter halo, a kind of invisible cocoon surrounding a galaxy. You can't see it, but you can feel its pull. Without it, galaxies would fall apart, stars would slingshot into intergalactic space. The universe would be a scattered mess of broken spirals and orphaned star clusters. Dark matter pulls, it clumps, it attracts. It's the scaffolding that allows galaxies to form and stick together. Simulations of the universe's structure look like cosmic webs only when dark matter is included. And now, across the dark void, you float toward the polar opposite, dark energy. Where dark matter clumps, dark energy spreads. Where dark matter pulls, dark energy pushes. While dark matter makes galaxies more bound, dark energy drives them apart. If the universe were a Netflix drama, these two would be the emotionally repressed siblings with unresolved tension and wildly incompatible goals. Dark matter wants structure, galaxies, clusters, filaments. It likes a cozy universe, gravity-bound and orderly. Dark energy is the agent of chaos, gently, inexorably stretching the fabric of space itself, weakening the bonds that dark matter worked so hard to maintain. And yes, they both happen to be dark, but only because neither interacts with light. That's like calling a fish and a stealth bomber the same because they're both hard to spot underwater. The similarity ends at invisibility. Here's your quirky tidbit of the night. For a while in the mid-20th century, some physicists tried to make one exotic particle explain both dark matter and dark energy. Sort of a unified theory of cosmic awkwardness. But this idea was like trying to use bubblegum to fix both your plumbing and your taxes. It didn't hold up. Instead, what we now have is a two-component dark sector. Dark matter, 27% of the universe, provides gravity, holds galaxies together, doesn't interact with light or regular matter except through gravity. Dark energy, 68% of the universe, causes accelerated expansion, acts like a negative pressure, doesn't clump, doesn't pull, just expands. You do the math, and that leaves only about 5% for everything else, everything visible, stars, gas, planets, you. Let that sink in. Everything you've ever known, touched, or seen makes up less than 1/20th of reality. The rest is dark. And the two biggest parts? Completely different from each other. Now you float into a visualization of the cosmic timeline. Early on, dark matter was the MVP. Its gravitational pull helped sculpt the web of galaxies. Dark energy, if it existed at all back then, was barely noticeable. But as the universe expanded and matter thinned out, dark energy began to dominate, like the quiet kid in class who suddenly inherits the school. Now, in this era, the one you're living in, dark energy has taken the wheel. It's no longer a background player, it's shaping the fate of everything. But here's the twist. We still haven't directly detected either of them. Dark matter has left its fingerprints all over galaxy rotation curves, lensing patterns, and cosmic structure. Dark energy has twisted supernova measurements, warped the cosmic microwave background, and shaped expansion curves. But no one's ever caught a particle of dark matter in a lab. No one's ever measured dark energy in a test tube. You might be asking, could one of them not exist? Some alternative theories, like modified gravity, suggest that dark energy might be an illusion, a sign that general relativity breaks down at large scales. Some go further and try to explain away dark matter too. But those models, they're like trying to rewrite the dictionary because you found a typo on page 7. Possible? Maybe. But they need to explain everything else that works so well under the standard model. Still, the debate goes on. Dark matter remains elusive, dark energy even more so. And you? You're stuck in the middle of the strangest love triangle in physics, where the two dark forces that rule everything refuse to acknowledge each other. They're not friends, they're not allies, but they're both absolutely essential to understanding what the universe is doing and where it's going. So you drift again, pulled by one force, pushed by another, realizing that the tension between dark matter and dark energy isn't just theoretical. It's the reason anything exists at all. You drift now along the long curling timeline of the universe, like a ribbon of light stretching through darkness, stitched with stars and shadows. The story of everything, written not in pages but in particles, gravity wells, and this ever-present quiet force we call dark energy. Let's rewind your cosmic journey for a moment. You hover at the beginning, at the spark, the Big Bang. Not an explosion in space, but the expansion of space itself, from an unimaginably hot and dense state. Time begins. Energy floods into the void. The infant universe is a glowing soup of particles and radiation. And yet, even here, perhaps even especially here, the seeds of everything to come are already present. You trace the expansion from those early moments forward, through billions of years. You see the formation of the first atoms, the first stars, the first galaxies twirling into place like embryonic whirlpools of light. The universe expands, but for a long time gravity is in control. Dark matter pulls, clumps, builds structure. Dark energy, if it's even around yet, is quiet, dormant, like someone in the back of the auditorium waiting for their cue. But the cue does come. Roughly 9 billion years after the Big Bang, about 4.5 billion years ago from your current moment, dark energy starts to take over. The balance shifts. The universe has grown so vast and spread out that gravity's influence starts to fade. There's just not enough matter density left to slow the expansion down. And that's when dark energy, still silent, still unseen, begins its domination. You float at that cosmic tipping point, where the rate of expansion, once decelerating, begins to accelerate. It's subtle at first, barely a difference in the stretch of space-time, but over time, the difference compounds. The galaxies begin to drift apart faster, the voids between them grow, and the expansion, it doesn't stop, it speeds up. This is the era we live in now, the dark energy era. Gravity still runs the show at small scales. It keeps stars orbiting stars, galaxies dancing, your feet on the floor. But at the grandest scale, dark energy is the choreographer. It decides how much space stretches between the galaxies. It decides the shape of the future, and that future is lonely. You float toward a far-flung epoch, hundreds of billions of years from now. By then, most galaxies beyond our local group, our galactic neighborhood, will have vanished beyond our cosmic horizon. Their light will no longer be able to reach us even if we wait forever. It's not that they've moved through space. It's that space itself has expanded so fast that their photons are permanently out of reach. Imagine running toward a finish line that moves away faster than you can sprint. That's what future astronomers will face, a shrinking window on the observable universe. You coast beside a future Earth, if it still exists, circling a redder, dimmer sun. Its sky looks oddly empty. No Andromeda, no Virgo cluster, just the merged remains of a few local galaxies. To those future observers, the universe will appear static, cold, bounded. They'll think they're in a lonely island cosmos because all the evidence of expansion is gone. And this isn't poetic exaggeration, it's an observational reality. Historians still argue whether future civilizations, billions of years from now, will be able to rediscover the truth. Will they have the tools to detect dark energy with no visible cosmic expansion? Will they even know that galaxies used to be more numerous? The idea that the cosmos can hide its own history is, frankly, rude. But it's also elegant in its own haunting way. The universe evolves, it changes, and dark energy writes the ending, not with fireworks, but with distance, isolation, the final creeping silence of space expanding forever. Of course, this assumes that dark energy remains constant. If it's quintessence or some other dynamic field, then all bets are off. The acceleration could slow, stop, or even reverse. The universe could collapse in a big crunch, bounce back in a new bang, or do something no one has yet imagined. But if dark energy behaves the way it seems to now, constant, uniform, unchanging, then the timeline looks something like this. Trillions of years from now, star formation ceases. There just won't be enough cold gas left to spark new light. Quadrillions of years pass. White dwarfs slowly cool into black frozen cinders. The last stars flicker out. Octillions of years go by. Even black holes begin to evaporate via Hawking radiation. They fizzle out into soft hissings of energy, whimpers in the dark, and finally, after unfathomable time, the universe reaches heat death. Maximum entropy, no usable energy, just an ocean of cold particles in ever-expanding space. A thermodynamic graveyard. You hover in that future now, not frightened, just still. No light, no warmth, just the memory of motion, of expansion, of a time when stars danced and galaxies flirted. The universe didn't explode or collapse, it just stretched itself into silence. Here's your quirky moment. In some timelines, it's been proposed that highly advanced civilizations could use stellar remnants to store information, building machines that outlast the stars themselves. Digital structures that persist even as matter decays. A cosmic library in the dark. Whether that's plausible or just theoretical fan fiction is anyone's guess, but the fact that we're even asking, wild. So you float back now, returning from the distant future, back through the long age of stars, past our current moment where dark energy has just begun to flex its influence. The universe is still busy, still bright, still noisy with gravity, but the end is written in the stretch. The timeline has bent toward acceleration, and unless something changes, it's only going to bend more. You look out into the dark where galaxies are already sliding beyond reach, and you whisper a quiet truth. The faster we learn about the universe, the faster it seems to be leaving. You drift now alongside machines, cold, silent, and impossibly delicate. Not ships, not satellites in the traditional sense. These are instruments of precision, launched with one goal in mind: to measure the immeasurable, to stare across billions of light years and whisper, there it is. There's the dark energy. Of course, they don't find dark energy directly, they can't. It doesn't emit, reflect, or block light. It doesn't gather or scatter. It doesn't even leave a calling card. So instead, we look for its effects, its fingerprints on the cosmos, its slight distortions of everything we can see if you know where and how to look. You float beside the Hubble Space Telescope first. It wasn't built with dark energy in mind. Launched in 1990, well before the acceleration discovery, but it became instrumental in confirming it. By observing Type Ia supernovae, the same standard candles that originally revealed the accelerating universe, Hubble refined their distances, made the redshifts sharper, turned suspicions into data. But Hubble was just the start. You drift now toward a wave of newer, hungrier missions. Cosmic sleuths, built to hunt the shape of the universe itself. There's WMAP and Planck, which you've already passed, microwave background mappers that revealed, with exquisite resolution, the universe's overall composition. Then came DES, the Dark Energy Survey, a 5-year effort using a telescope in Chile to map the positions of over 300 million galaxies, looking for clues in their clustering and lensing. Because that's the secret. Dark energy may be invisible, but it changes how everything else moves. You glide now through a field of galaxies, not randomly scattered, but woven into filaments, strands, and knots. This large-scale structure evolved over billions of years under the influence of gravity. But dark energy changes that evolution. It slows the growth of structure. As the universe expands faster, matter has less time to collapse under gravity. Clusters don't grow as quickly. Voids stretch more than they should. By comparing how galaxies cluster now versus how they should have clustered under gravity alone, scientists can detect the subtle hand of dark energy at work. You pass over simulations being run on supercomputers the size of buildings. Each particle represents a galaxy, or a dark matter halo, drifting, clumping, spreading under the influence of different dark energy models, lambda CDM quintessence, phantom fields. Some models produce beautiful, orderly webs, others spin into chaos. Then you glide past Euclid, a European Space Agency mission launched to map 2 billion galaxies across a third of the sky. Its job? To chart the geometry of the universe and test whether dark energy is really a constant, or something stranger. And coming soon, you see the future in the form of the Nancy Grace Roman Space Telescope, NASA's upcoming flagship mission, nicknamed the Hubble on steroids. It will peer deeper and wider using gravitational lensing and baryon acoustic oscillations, we'll talk about those soon, to trace how expansion has evolved over time. Historians still argue whether we're in the precision cosmology era or just fooling ourselves with prettier graphs. But one thing's certain, the sheer number of measurements we now have, supernova distances, galaxy redshifts, cosmic background wiggles, lensing distortions, forms a web of evidence too detailed to ignore. Let's pause for a moment to appreciate one of the cleverest tricks used to measure dark energy: weak gravitational lensing. You drift beside a massive galaxy cluster now. Its gravity warps the space around it, not just pulling on matter, but bending light itself. Distant galaxies behind it appear stretched, squished, or arced into little smears called Einstein rings. That's strong lensing. But weak lensing, that's subtler. It's the tiny distortions in the shapes of millions of background galaxies caused by less massive clumps of matter, dark matter halos, filaments, cosmic fluff. By statistically analysing how galaxy shapes are ever so slightly skewed across the sky, cosmologists can map the invisible scaffolding of the universe. And here's where dark energy steps in. If dark energy is accelerating expansion, then the growth of structure slows down, less clumping, weaker lensing signals. By comparing lensing across different distances and times, you can see the fingerprint of dark energy slowing gravity's roll. That's like figuring out the recipe of a cake just by watching how the oven expands the batter, and yet, somehow, it works. Now for your quirky tidbit of the night, one method being developed to measure dark energy is called intensity mapping, which essentially involves using the light from neutral hydrogen across vast cosmic volumes to chart large-scale structure. Kind of like doing an MRI of the universe using radio waves. It's still early days, but if it works, cosmic cartography at a scale we've never achieved. Of course, there are challenges: dust, noise, calibration issues. Telescopes are imperfect, and the universe is annoyingly messy. Galaxies do unexpected things. Supernovae vary slightly. Data gets blurry with distance, and the farther out we look, the fuzzier things become. Not just because of space, but because of time. We're not just looking far, we're looking back. The light we catch tonight left its source billions of years ago, and the farther we reach, the harder it is to disentangle what's real, what's illusion, and what's a byproduct of our own assumptions. Still, we build, we observe, we model, we send machines to high mountain plateaus where the air is thin and clear. We launch satellites beyond the atmosphere to stare without blinking. We crunch numbers for months, run simulations for years, and recheck our math again and again because the stakes are cosmic. What we're trying to do, ultimately, is reconstruct the entire expansion history of the universe. A cosmic diary, written in redshift and light curves and lensed galaxies. And with that diary, we hope to answer the ultimate question. What is this thing that's stretching space apart? And will it ever stop, or change, or do something worse? You pause for a moment, watching a telescope array scan the night sky, collecting photons older than Earth itself, each one a data point, a breadcrumb in the dark. Measuring the unmeasurable isn't easy, but it's the only way we'll ever know how the story ends. You drift now toward the edge of comfort, the place where even Einstein starts to look a little shaky. Not because he got anything wrong, necessarily, but because the universe is acting, suspiciously. And when 100 years of physics doesn't explain what you're seeing, there's only one thing to do. You question the rules themselves. Tonight you float into the realm of modified gravity, a theoretical jungle where general relativity, the towering achievement of 20th century physics, is quietly being poked with sticks. The idea is simple, in a terrifying sort of way. Maybe dark energy doesn't exist. Maybe it's not a thing at all. Maybe what we're seeing, the accelerating expansion, the changing structure of the cosmos, isn't being caused by some invisible force, but by gravity acting differently on large scales. You glide now through the towering equations of general relativity, Einstein's masterwork. They describe how matter bends space, and how that bending tells matter how to move. It's a beautiful geometric dance, and it works extremely well. GPS satellites rely on it. Black holes obey it. The orbit of Mercury makes sense because of it. We've tested it with incredible precision in the solar system. But here's the catch. Most of those tests are on small scales, solar system, binary stars, maybe a close galaxy or two. Once you zoom out to the cosmic level, hundreds of millions of light years, you're in uncharted waters. And some physicists have dared to ask, what if gravity changes at those scales? What if Einstein's equations are an excellent local recipe, but they leave something out on the grandest stage? So you float into a space filled with alternative ideas, each with its own flavour of rebellion. The most famous of the bunch? MOND, or modified Newtonian dynamics. Originally proposed in the 1980s to explain galaxy rotation curves without invoking dark matter, MOND tweaks Newton's laws at very low accelerations, and while it mostly aims to replace dark matter, some expanded versions of MOND have been proposed that also account for dark energy behaviour, sort of a one-stop shop for cosmic weirdness. But MOND isn't alone. You now glide through a stack of papers labelled F of R gravity. These theories modify Einstein's original field equations by changing the mathematical function that relates matter to spacetime curvature. Instead of a tidy linear relationship, you get something more complex, something that might mimic the effects of dark energy without needing an actual vacuum energy component. Then there's Brans-Dicker theory, an early attempt at introducing a variable gravitational constant, meaning gravity could vary over time and space, depending on some underlying scalar field. It's fallen out of fashion, but like all good ideas, it left fingerprints on later work. And then there are the truly bold theories, like DGP gravity, named after Dvali, Gabardadze and Parati, which proposes that our 4D universe is actually a brain embedded in a higher dimensional space. In this model, gravity can leak into extra dimensions, becoming weaker on large scales, which might explain why the universe expands faster than expected. Yes, that sounds like sci-fi, but string theory and brain cosmology were genuinely hot topics for a while, and their mathematical bones still get used in current research. Historians still argue whether any of these modified gravity theories have actually improved on the predictions of general relativity, or just added more complexity without solving the real problem. But the very act of questioning Einstein, that's not done lightly. It's worth pausing here to ask, why would gravity need modifying at all? Why fix something that already explains so much? Because dark energy, for all its mathematical usefulness, is a deeply unsatisfying answer. It's not predicted by the standard model of particle physics. It doesn't fit naturally into quantum field theory. And the vacuum energy problem, where the math predicts a value 120 orders of magnitude too high, remains a gaping wound in our understanding. So for many theorists, modifying gravity isn't a betrayal of Einstein. It's an act of respect, an acknowledgement that even the greatest ideas must evolve when the universe demands it. You glide now through simulations comparing different models. One uses standard general relativity with a cosmological constant. Another uses a modified gravity law, something nonlinear and strange, but tuned to match what we observe. In some versions, galaxies form just a little faster. In others, large-scale structure takes longer to grow. In a few, the cosmic microwave background patterns begin to shift. Subtle differences, but potentially measurable. And here's your quirky tidbit of the night. One model called TeVS, short for tensor vector scalar gravity, was so complicated that its own creator, Jacob Bekenstein, joked that even he wasn't sure it made sense. It tried to merge MOND with relativity to explain both dark matter and dark energy effects. It mostly didn't catch on, but its boldness still gets a nod from theorists who enjoy swinging for the fences. Of course, modified gravity has its own problems. Many of these theories introduce extra degrees of freedom, fields or particles or parameters that need fine-tuning to not break everything else. Some predict observable side effects, faster-than-light gravitational waves, changes in the strength of gravity over time, violations of the equivalence principle that we simply don't see. And the final blow? When gravitational waves were directly detected in 2015 by LIGO, and again when a neutron-star collision was observed with both gravitational waves and light, it allowed scientists to test gravity in brand new ways. Some modified gravity theories predicted gravitational waves would travel at different speeds than light, but they didn't. So those theories, out. You float in that realization now that most modified gravity models either fail to match observations or succeed only by becoming indistinguishable from standard dark energy, a kind of theoretical snake eating its tail. Still, people keep trying, because deep down, the mystery remains. Dark energy, as currently understood, is just a placeholder, a workaround, a term in an equation that says something's happening and we don't know why. So whether it's a new particle, a rolling field, or a tweak to the laws of gravity themselves, the question stays the same. What's pushing the universe apart? And does that push come from within space, or from the rules that govern it? As you float once again into open sky, past blackboards and beamlines, past theories scribbled and crossed out, you carry that uncertainty with you, because the longer you stare into gravity, the more it starts to blink. You're drifting now along the edges of reason, where the universe splits, not metaphorically, but literally. One reality becomes many. It's quiet here, not because nothing is happening, but because everything is happening. Every possible version of the cosmos exists in parallel, like an infinite stack of dreams, each whispering a slightly different version of reality. Welcome to the multiverse problem, where dark energy becomes not just a force, but a cosmic lottery ticket, and depending on which universe you're in, the numbers may or may not have come up in your favour. Let's start with the question that gnaws at everyone in the back of the mind. Why is dark energy so small, but not zero? The cosmological constant, if it were a true constant, could have taken any value. But instead of being huge, strong enough to blow the universe apart before galaxies could form, or zero, leaving us with an ever-slowing cosmos, it has this tiny, finely tuned value. Just enough to accelerate the expansion, but not so much as to ruin everything. Why? You float through this riddle now, spinning gently through equations that don't offer a satisfying answer. It's like the universe is perfectly balanced on the edge of a knife, and that knife just happens to allow life to exist. Galaxies, stars, chemistry, you. And this is where the idea of a multiverse tiptoes in. What if the value of dark energy isn't fixed at all? What if it varies across different regions of an unimaginably vast reality, each region with its own version of the laws of physics? What if our universe is just one bubble in an infinite cosmic foam, and in every bubble the properties of space itself are a little different? You coast now through the concept of eternal inflation, a theory born from attempts to explain the rapid expansion of the universe in its first fractions of a second. Inflation says the universe expanded at blistering speeds early on, and in some versions that expansion never fully stopped. Pockets of inflating space keep bubbling off, forming countless baby universes, each with its own physics. And in some of those universes, dark energy is stronger, expansion is faster, galaxies never form, no stars, no planets, just pure stretch. And in others, dark energy is negative, causing those universes to collapse almost immediately after forming. Again, no structures, no observers. But in a few rare cases, the number just happens to be just right. Not too much, not too little. Goldilocks expansion, you're floating in one of them. This idea, called the anthropic principle, suggests that we observe the value of dark energy we do, because we couldn't exist in any universe where it was different. It's not that the universe was made for us, but that only in certain types of universes could anyone be around to ask the question. Historians still argue whether the anthropic principle is a meaningful insight or just a cosmic shrug. It doesn't explain why the value is what it is. It just says, well, we're here, so it must be this way. Philosophically slippery but hard to refute. Now here's where things get really strange. In some theories, especially those coming out of string theory, there are not just a few universes, but as many as 10 to the power of 500 possible versions. Each one a different solution to the equations that describe the geometry and energy of space, different values for gravity, particle masses, maybe even entirely different dimensions, and in each one a different value of dark energy. You glide past a wall of post-it notes representing these possibilities, some universes quickly ripped apart by runaway expansion, others stillborn in a gravitational collapse, and a few, just a few, where the conditions are just stable enough to produce complexity. Like ours, you float through the so-called string landscape, a theoretical field of possible vacuum states, each a different version of physical reality. And here's your quirky tidbit. One of the challenges of this idea is figuring out how the universe would choose which vacuum to settle into. Some physicists joke that the universe rolled a 10 to the 500-sided die and just got lucky. Others say it settled randomly, like condensation forming on a window guided by quantum fluctuations. Of course, there's no way yet to observe these other universes. If they exist, they're separated from us by regions of space, expanding faster than light can cross. We'll never see them, never touch them, never send a probe. They're forever out of reach, which raises a pretty sticky issue. Is this science? If we can't test it, if we can't falsify it, if the multiverse lies beyond our observational capabilities, are we still doing physics? Or are we doing something closer to metaphysics, dressed up in math? Some argue the multiverse is just the logical conclusion of inflation, quantum mechanics, and string theory all taken seriously. Others say it's a dangerous step, a philosophical black hole that lets us explain anything and therefore nothing. Still, the multiverse remains a compelling explanation for the fine-tuning problem. Not just for dark energy, but for all sorts of constants in nature. The mass of the electron, the strength of the strong force, the number of spatial dimensions. In a multiverse, you don't need a reason. You just need enough tries. And here's the quiet, humbling part. If the multiverse is real, if countless other realities really do exist, each with different physics, then the universe you live in might not be special. It might just be survivable. That's a very different flavour of awe. One that makes you feel small not because you're insignificant, but because you're rare. A statistical outlier in a sea of sterile chaos. A fluke that learned to ask questions. So you float here for a moment, between the expanding boundaries of what can be known and what must be accepted. Maybe dark energy is random, maybe it's selected, maybe it's unique, maybe it's just one roll of the die, and maybe the reason we're here is because we're in the one version of reality where someone could be. You drift now through a space filled not with galaxies or particles, but with equations, elegant, dense, and maddening. It's quieter here than anywhere you've been on this journey. Not because there's nothing to see, but because everything you're seeing is invisible, theoretical, and debated with ferocious calm by physicists in windowless rooms. This is where dark energy might not be real, at least not in the way you think. You hover here at the crossroads of two uncomfortable possibilities. 1. Dark energy is a genuine physical force, some kind of substance, field, or property of space that exists and acts on the universe. 2. Dark energy is a glitch, a misunderstanding, a sign that our math, our models, or even our foundational assumptions about the cosmos are just a little off. It's the cosmic equivalent of discovering that your GPS has been sending you to a fake Starbucks this whole time. Everything looked right. The coordinates made sense, but something in the system lied to you and now you're sipping hot foam in a furniture store. Let's start with the first idea, the one we've leaned on this whole time. That dark energy is the energy of the vacuum. You've heard it before. Even empty space has energy due to quantum fluctuations. This energy would produce a gentle, constant pressure, just like the cosmological constant Einstein reluctantly introduced. That's been the backbone of our best cosmological models for decades. But there's a massive problem. If you calculate the expected vacuum energy using quantum field theory, the same theory that accurately describes particle physics with absurd precision, you get an answer that's about 10 to the 120 times too big. This is famously the worst theoretical prediction in the history of physics, ever. Historians still argue whether it's fair to call this a prediction at all, since it's clearly not matching what we observe. But whether it's a catastrophic failure or a misunderstood success, the fact remains. Something doesn't add up. You drift through the wreckage of this problem now, watching equations collapse under their own inconsistencies. It's like trying to balance your checkbook and realizing your income includes 50 ghost paychecks for jobs you never worked. Some physicists argue this discrepancy points to a missing mechanism, something that cancels out most of the vacuum energy, leaving just a tiny residual amount. But no one can say what that mechanism is, or why it would cancel exactly 119 orders of magnitude and leave one behind. That's like throwing a dart from the moon and hitting a bullseye on Earth, blindfolded with no arms. So others propose something more radical. What if our assumptions about gravity and space-time are flawed? You glide past a set of alternative models, the kind that don't try to add new forces, but instead try to rethink how we describe space itself. In these models, dark energy isn't a thing that exists in space, it's a side effect of how we model space. Maybe, they argue, the universe is not as homogeneous and isotropic as we assume. Maybe the apparent acceleration is caused by inhomogeneities, that is, large-scale structures like voids and walls warping our measurements. In some interpretations, light travelling through uneven cosmic terrain gets subtly distorted, giving the illusion of acceleration when in fact, it's just passing through bumpy spacetime. This idea is called the back reaction scenario, and while elegant, it's also controversial. Most cosmologists think the effect is too small to explain the observed acceleration, but the fact that it's even a contender shows how far people are willing to stretch when the numbers don't behave. Another group suggests that time itself might be evolving in a non-linear way. This isn't time travel, don't get excited. It's more like the possibility that our perception of time's flow is being warped by cosmological parameters we don't yet understand. If time slows or stretches subtly as the universe expands, it might trick us into thinking distances are increasing faster than they are. Wild? Yes. Impossible? Number. Here's your quirky tidbit of the night. A few fringe thinkers have even proposed that the acceleration is an illusion created by our position in the universe, that we just happen to live in a massive cosmic void, and the redshifts we observe are being skewed by the density differences between our region and the cosmic average. It's called the void model, and while it's a minority view, it's oddly persistent. But whether it's back reaction, a void, weird time, or extra dimensions playing hide and seek, the core motivation is the same: to explain the data without inventing a new form of energy. Because inventing new physics is risky. You can patch the model, sure, but at what point are you just duct taping over your ignorance? Still, there's a problem with these alternatives. They must match all the observations that dark energy already explains: supernova redshifts, galaxy clustering, the CMB, baryon acoustic oscillations, structure growth rates, and so far, no alternative model has done that perfectly without invoking some kind of fudge. And so, most cosmologists stay in a kind of uneasy truce with dark energy. They acknowledge its mystery, but they keep using it in their equations. Because frankly, it works, even if no one knows why. It's like driving a car that runs beautifully, but every time you lift the hood, there's just a bunch of wires stapled to a potato. You can't explain it, but you're still getting to work on time. You pause now, floating in this intellectual fog. It's the uncomfortable space between explanation and admission, between we've discovered something amazing and maybe the math is broken. And this is where science often lives, not in the certainties, but in the tension between function and understanding. We know dark energy is doing something. We can measure its fingerprints on space-time, but whether it's a new force or a symptom of bad math, still unclear. Maybe the universe is expanding faster because something is pushing, or maybe it just looks that way because we're reading the wrong map. Either way, you drift forward with a strange thought. What if dark energy isn't real, but it's still true? You drift now through a quiet corridor of thought, where the future isn't some far-off abstraction. It's a question of when. The galaxies still shimmer in the distance, but something has changed. You can feel it. Space is stretching, yes. But what if the rate of stretch isn't steady? What if the force responsible for all this expansion, the dark energy you've come to know and distrust, shifts? Not a lot, just a little. Enough to ruin your whole day. Because tonight, you're going to explore a very real, very unnerving possibility. What happens if dark energy changes tomorrow? We've spent the last 18 sections assuming dark energy is either a constant or a slowly evolving field. It's gentle, subtle, more patient than gravity, less rude than black holes. But there's nothing in the laws of physics that requires it to stay that way. So, what if it doesn't? You coast through this thought like a leaf in a rising tide. Maybe dark energy is dynamic, something like quintessence, a field rolling ever so slowly across its potential energy landscape. Maybe it's behaving itself now, but it could just as easily start evolving more quickly. Maybe it could spike, fade, reverse, or glitch out entirely. You pass a field equation trembling under the weight of this question. You watch cosmologists run simulations of alternate futures. They tweak the value of W, that sneaky little parameter that tells us how dark energy behaves. If W stays at -1, we're in lambda land, a universe of smooth, accelerating expansion forever. But if it dips even slightly, say to -1.1, you enter phantom territory. And as you learned earlier, that leads to something dramatic. The big rip. Let's recap. If dark energy grows stronger over time, the expansion accelerates faster and faster, eventually tearing galaxies apart, then solar systems, then atoms. If W slips below -1 and stays there, you get a deadline, a countdown to the final expansion. So what if that shift happened tomorrow? You hover over Earth, where no one notices at first. Galaxies still look distant and peaceful, but deep in the math, things are no longer right. The acceleration begins to increase. Over the next few million years, galaxies start to vanish beyond the cosmic horizon faster than ever. Star formation slows. The night sky begins to dim, not just from entropy, but from abandonment. In 1 billion years, galaxy clusters are shredded. In 2 billion, planets are ripped from their stars. By the 3rd billion, the stars themselves are torn apart, gravity no longer strong enough to hold them together. And near the end, even atomic nuclei can't hold. You pass through the simulation's final frames. Silence. No structure, no memory. Just particles rushing away from each other across an ever-expanding canvas. Infinite, but empty. Of course, that's the extreme case. What if W shifts upward instead? Maybe toward -0.9 or -0.8. Now, dark energy becomes a little less powerful. Expansion slows. The future doesn't end in a rip. It just coasts differently. Maybe structure formation has more time. Maybe new galaxies have a chance. Maybe the universe gets a little more time to write its story. Or perhaps, wild thought, it shifts into positive pressure. Dark energy stops pushing, starts pulling. Suddenly, the balance tips back in gravity's favour, and that leads to another endgame, the big crunch. You float backward in time, in reverse, because that's what this would look like. Expansion slows to a stop, then reverses. Galaxies converge, clusters collapse, the universe heats up, light blue shifts, radiation intensifies, the sky fills with energy as everything falls inward. At the end, another singularity, perhaps followed by another bang, or just the end. Historians still argue whether any of these transitions could happen spontaneously. Could a quantum fluctuation tip the dark energy field into a new state? Could we live in a false vacuum, a local energy minimum that only pretends to be stable until it suddenly decays? You may have heard of this, vacuum metastability. It's the idea that the universe isn't in its true ground state, that it's perched on a ledge and could tunnel through a quantum barrier to a lower energy state. If that ever happens, a bubble of true vacuum forms, expanding at the speed of light, obliterating everything in its path. New physics, new constants, possibly no atoms, certainly no Netflix. And because it moves at light speed, you'd never see it coming. Comforting, isn't it? But back to the calmer possibilities. Let's say dark energy does change, but slowly. Over cosmic time, it decreases. Maybe it fades entirely. That could allow gravity to regain control, leading to a slow crunch. Or, more optimistically, it might bring the expansion to a gentle halt, a cosmic loitering phase. No collapse, no rip, just a universe that stops stretching and simply rests. There's even a poetic model for that, the big chill. Expansion continues but slows. Energy spreads thin, stars die, black holes evaporate, and what remains is a dark, frozen sea of photons and particles drifting forever in silence. Now here's your quirky tidbit. Some theorists once joked that if dark energy increased slightly, but not enough to cause a big rip, it might be used to accelerate time in specific regions of space, leading to localized fast-forward zones where entropy rises more quickly. It sounds absurd. It probably is. But someone wrote a paper, and in physics, that's practically an invitation. You float now in the uncomfortable possibility space where any change in dark energy could rewrite the entire future. And the truth is, we don't know if it will change, or if it can. All we know is that current observations show hovering very close to -1. Not clearly above, not clearly below, just right on the line. And whether that's a coincidence, a sign of something deeper, or a cosmic red herring, no one can say, so you drift back toward the present. The skies still sparkle, the galaxies still drift, and the expansion, so far, holds steady. But tomorrow the universe might get curious. It might stretch a little faster, or stop altogether. You drift now toward the edge, not of space, but of certainty. You follow dark energy from its first whisper in distant supernovae to the warped patterns of the cosmic microwave background. You've watched galaxies stretch apart, floated through fields of phantom energy, questioned Einstein, and peeked into the quantum abyss. And here we are, after all the math, all the measurements, all the beautifully chaotic simulations, there's one haunting truth you can't quite escape. This mystery may never be solved. You pause now in a vast, still pocket of space. No galaxies, no stars. Just the silence between structures. It's here that dark energy feels most real. Not because of what it is, but because of what it does. Even in this emptiness, it expands. A soft push against nothing. A whisper against the void. It's been over 25 years since we first discovered the universe's expansion was accelerating. A quarter century of data, missions, models, and yet there is no agreed-upon mechanism, no confirmed particle, no definitive field, not even a satisfying theory that ties it all together. Maybe dark energy is a cosmological constant, the simplest answer, a fixed number built into the structure of space-time. It explains the data, fits the models, and requires no new physics, just an unreasonably small value. Or maybe it's a field, a dynamic thing changing slowly across time. That would explain why dark energy showed up late in the universe's timeline, why it started dominating only after matter had spread thin. Or maybe it's something stranger still, a sign that gravity is incomplete, that Einstein's equations, for all their brilliance, need a 21st century overhaul, not because they're wrong, but because they're too local, too tuned to our solar system, and not enough to the cosmic stage. You float now past all those possibilities, like passing signs on a road that might not lead anywhere. Every time we think we've found a path, the numbers ask more questions. The data says, close, but not quite. Some physicists have started asking a dangerous question. What if this is the limit of what we can know? Not because we're not clever enough, not because we haven't built good enough telescopes, but because the nature of dark energy itself may place it forever beyond direct detection. It may be a feature of space that leaves no trace, no fluctuation, no particle trail, just a gentle universal pressure that affects everything, but can't be isolated from anything. In that case, our best hope is inference, measuring how galaxies move, how light bends, how structures grow or fade, using cosmic archaeology to guess at the shape of the architect. It's like trying to understand wind by watching how trees sway, except the wind never gusts, never changes, and always moves just slow enough to stay suspicious. And yet, there's something elegant in that too. Here's your quirky tidbit of the night. Some scientists, usually the sleep-deprived ones, joke that dark energy might not be a thing at all. It might be a placeholder for a bigger realization we haven't had yet. The way 19th century physicists invoked ether to explain how light traveled through space, until Einstein came along and made the ether unnecessary. So maybe one day dark energy will be like that, a ghost we invented while fumbling through the dark waiting for a better candle. But for now, we live in a universe pulled apart by a force we can't explain, and maybe, just maybe, we don't need to. Science isn't always about answers. Sometimes it's about questions that are so good, so powerful, so endlessly deep, that asking them changes the way we see everything. That's what dark energy has done. It's reminded us that the cosmos isn't finished surprising us, that even after centuries of physics, we're still at the beginning, still floating in the fog, still listening for whispers at the edge of space. And that's okay, because the best mysteries don't scream. They hum, they wait, and they pull you forward faster than light can catch. The stars fade now, softly, without drama. You drift at the edge of everything we know, and beyond that, just silence. The journey is done. The ideas have swirled, the numbers have danced, and now it's time to let it all settle, like stardust sinking back into a calm galactic tide. Breathe in and out. Dark energy, whether it's a force, a field, a flaw, or just our favourite excuse for bad math, has left its mark. Not just on galaxies and space-time, but on you. You floated through 22,000 words of expansion, mystery and philosophical vertigo. And here, at the end, there's nothing left to chase, only stillness. The universe continues to expand, of course, but here, in this moment, you're weightless and unhurried. The great questions, the ones that bent your mind in Section 8, made your eyebrows twitch in Section 13, and raised a polite existential panic in Section 17, no longer feel sharp. They're soft now, rounded, echoes of curiosity instead of puzzles demanding solutions. This is where science becomes something gentler, not equations or telescopes, but wonder, not tension, but awe. Let it all fade. Let the names, quintessence, phantom energy, cosmological constants, fall away like leaves. Let the models dissolve, let even the stars dim. Because the best part of science is not always knowing. It's not knowing and still listening, still watching. So now, sink into the quiet between galaxies, the dark hum of expanding space, the cold poetry of a universe writing its own future, line by line, light year by light year. And in this endless stretch of silence and starlight, you're reminded, you don't need to hold the universe together, you just have to float with it. Good night.